Okay, everyone, let's get started. So the plan is on Tuesday, today I'm going to finish up the SPI material and might get started on another topic. And then on Tuesday, we'll assign the first lab, and then we're going to give you all day on Thursday to work on it. And I'm going to try to do the thing we normally do in this class is we have this cadence where I'll lecture on Tuesday, and then you'll have the class on Thursday basically to work on the lab and ask questions. So I think we're gonna try to stick to that schedule. Makes sense? So I'm not gonna, I have the lab almost ready to go out. I'll probably post it on Dropbox over the weekend, and then I'll talk about it in detail on Tuesday. Okay? All right, so last time we talked about pulse width modulation. Pretty simple idea. It's just basically a clock. It's a periodic clock signal, and it has a certain frequency, and the frequency is the reciprocal of the time from rising edge to rising edge, which is the period, right? And then the duty cycle is the percentage of that period that the signal is active high, right? Active 1 or true, right? High, right? And so the idea is that over time, this is interpreted as an analog signal. So in lab 2, we're going to generate a PWM signal and use it to brighten and dim LEDs, right? Which is a typical way to do that. Okay, and then we talked about interrupts, and this is more of a conceptual thing. I don't think we're going to actually use interrupts in the labs, but the idea is that an interrupt is a way for a device to get the CPU's attention, and then the CPU, in response to that interrupt, will service it using an interrupt service routine that could be in the operating system, or if you're doing bare metal programming, it's in the hardware abstraction layer, right? And there's different ways to set up interrupts. They can be basically one way, where you've got a wire that goes from the peripheral to the CPU, and then in that case, the interrupt could be configured to be active high, a level triggered, where the CPU responds to the interrupt being active high, or edge triggered, where the CPU responds to the rising edge or the falling edge. On the Arduino, or the Atmel 328P, you can actually configure that in the hardware, whether you want it to be level sensitive or edge sensitive, and if edge sensitive, it can be rising or falling edge sensitive. And that, of course, would depend on, you'd have to set that up according to what the peripheral is doing that you're connecting to your CPU. Okay, and then a better way to do it is to have an acknowledged signal, which avoids this problem of the CPU, or the peripheral rather, having to guess how long to hold the interrupt high, for instance. So in this case, if this is a level sensitive or level triggered interrupt, and the peripheral held it too high, so it inadvertently triggered 2 interrupt service routines. And in this case, the interrupt tried to trigger 2 interrupts using an edge-triggered interrupt mechanism, but the CPU, only executed 1 interrupt service routine because it took longer to run that routine than the peripheral expected. So that's a lousy way to do it, but that's how Atmel does it. Real CPUs do it this way, where there's an acknowledgement mechanism, where there's a feedback line from the interrupt controller back to the peripheral that allows the CPU to indicate to the peripheral when it begins the interrupt service routine and also when it ends it. So the acknowledgement is usually high for a period of time corresponding to the runtime of the interrupt service routine. And that way, the peripheral knows when to drop its interrupt request and also when to wait before issuing the next one, right? So that's like a handshake that goes on there. Okay, so then we talked about, so that's, as I mentioned last time, that's from the software perspective. So if you're writing software to talk to hardware, you have to know about those things. From the hardware perspective, we have these interface channels and protocols, and there's a whole bunch of different types of protocols. It depends on how long you're going and how fast you want to be able to send data through that channel. And they're set up as channels typically, where a channel is multiple physical wires, right? So the first one we talked about was SPI, which stands for Serial Peripheral Interface. This is a very common interface to use for lightweight, cheap, low-power systems like Arduinos, for instance. And it is a serial protocol, meaning that it sends 1 bit at a time. So there's only 1 wire to send data, but then it's bidirectional, so there's 2 wires for 1 bit each going in either direction, right? So there's an outgoing wire and an incoming wire. And it's also a synchronous protocol, which means that the clock signal is embedded in the channel and it's driven by the master. So SPI is also a single master type of interface. You can only have one entity on an SPI channel that initiates communication. And then you can have one or more slaves that respond to it. Usually there's just one slave with SPI. It's kind of uncommon to have multiple slaves, but I'll talk about how you can do multi-slave. But so far I've just talked about single master, single slave. So the master sends out the clock, the slave select, which turns the channel on, and the outgoing bit, the MOSI, master out, slave in, which is the signal that goes from the master to slave. And the slave just has one output signal called MISO, which is the master in, slave out, which comes back to the master. So there's 4 total wires. And then we looked at some timing diagrams. So I think you guys told me last time you've seen these before. So one of the reasons I cover this is to understand interfacing, but also it's great practice to be able to read these timing diagrams, because these are pretty common whenever you have hardware communicating with each other. So you've got here the horizontal axis is time, and then you've got the 4 signals that are laid out vertically, and each of these signals is a single bit, so they can be high or low, right? Dotted lines represent moments of time, instants of time, snapshots of time, right? So the slave select goes low and then goes back high because it's active low. So if you count the number of cycles that slave select is low, in this case it's 8, because this is an exchange where 8 bits flow out from the master and 8 bits flow into the master, right? So there's 8 cycles in this case. It doesn't have to be 8 cycles, but generally it's going to be a multiple of 8 cycles whenever you do one of these, whenever you activate the bus. So this is a single exchange of 1 byte between the 2 sides of the channel, and thus its slave select is active for 8 cycles. You notice the clock is kind of dead until the slave select is activated, and then it goes dead again after the slave select deactivates. I don't know why that's done. Probably maybe to save power, or maybe it makes it easier to design the transceivers. And then there's the MOSI and MISO. Now the challenge here is we're going to ask you on the quizzes to read these bits. So the idea is depending on how the timing diagram was generated, and I generated these actually from, there's actually a package, a LaTeX package called, I forget what it's called now. It's built on top of TEEX. But anyway, I generated these from LaTeX. So I wrote a program that generates the LaTeX code, and then it converts these to PDF, and then I capture the PDF and put it in the slide as a raster graphic. But depending on how it's set up, and depending on how the channel is configured, sometimes these dotted lines will intersect the transitions, right, of the data. And that's actually, I think, makes it a little easier to read, because then you just read the state of the signal between the dotted lines, right? But other times when you look at these timing diagrams, the dotted lines will actually be offset by a half a cycle, in which case the dotted lines will kind of intersect the midpoint, right? And that's where the actual hardware would be reading the state of the signal, right? Right in between the transitions, right? But as a human being, I think it's easier to read it if you can look between the transitions and just see if it's high or low. Does that make sense? Okay, so my point is that you have to kind of get used to how to read these, but basically it's pretty easy to see here. It's 1, 0, 1, 0, 0, 0, 1, 1, right? And according to the header here, it should be read most significant bit first. So those 8 bits should be read from left to right, right? Makes sense? Most significant to least significant. Okay, and then of course C-pole 0, well that's obvious because you can see the clock is 0 at the beginning, and C-fa is 0, and that one's a little less obvious, but you can see that the first transition of the clock happens when the bit line is stabilized, right in the middle of the 2 transitions. So that means C-fa is 0. Now if C-fa were 1, the impact of that would be the clock would be shifted back 1/2 cycle, or the data would be shifted forward 1/2 cycle, right? So let's look at an example of that. Okay, which one is it? So if CFA is 1, like over here, you could see that, yeah, the clock is actually shifted back 1/2 clock cycle from the previous design waveform I showed you. And the way I know that is because you could see that, oh no, actually, wait a minute. No, I'm sorry, I was wrong. The data is shifted to the left, right? Because see, the clock, the first edge of the clock is happening 1/2 cycle after slave select goes low. That always is the case, right? The difference is the data. If you look at when the data changes, you can see that you see this gray area here. There's more gray here than there is here, right? So when CFA is 1, the data is actually taking a 1/2 clock cycle before it starts driving, before it starts asserting the data, right? And this gray area means don't care. It means, you don't know if the data line would be high or low there because we don't care and it's not relevant, right? So you can see that the data kind of chills for an extra 1/2 clock cycle before it snaps into action here when CFA is 1. And so the effect of that is that the hardware is expected to read that on the second edge of the clock. And we don't know if the second edge of the clock is rising or falling without knowing C pole, right? So the second edge of the clock would be a rising edge if C pole was 1, right? Because the clock would start out 1, the first edge would be falling, the second edge would be rising, right? If C pole is 0, the second edge would be a falling edge because you start out 0, then you go to 1, and then back to 0, right? Make sense? Okay, so you have to, generally the way this works is, in your Arduino, you have to configure its SPI transceiver, which is a hardware circuit, right? You might say, well, can't you do this with software? You can. If you do this in software, it's called bit banging. That's when, if you have control over individual pins, GPIO pins, like basically just digital pins that you can set with software commands. In Arduino, it's just write pin, I think. Write pin, read pin, right? Then you could do this in software, in which case they call that bit banging, which is where you do software control. But generally, you'd have a hardware circuit that controls all this. So from the software perspective, you're going to do a programmed I/O write in software. You're going to write a control register in software. So software is going to do a store instruction into the hardware SPI controller, and then the hardware SPI controller is going to do all this stuff for you. So that way, you don't have to burden the CPU with trying to, synchronize to a clock, right? Does it make sense? Now you might say, well, I mean, it's kind of impossible for that, right? Because CPU can really only execute like 1 instruction per clock. How could you have enough instructions per clock to track these transitions through? Well, no, because keep in mind the CPU's clock is going to be faster than the SPI clock. There's 2 clocks we're talking about now, right? The CPI clock on an Atmel chip is 16 megahertz, whereas this is going to run at a megahertz at best. So the CPU is going to be able to execute like maybe 16 instructions for every clock cycle on this bus. So in theory, you could bit bang this. It's just, usually it's not done because it would take the CPU's entire attention to see those transactions through, at least a low speed CPU, right? So that's why they use circuits to do that. Of course, you're limited in the number of circuits you have too, though. Like on an Atmel 328, there's only 1 SPI channel. If you need more than that, then you're going to have to bit bang the additional channels. You just don't have enough I/O on that chip, right? Yes?
Just go fast on this to introduce lab 1 so they could start it today.
I don't have it ready. And no one tested the waveform stuff, I assume, right?
Okay.
So
But you have a blog.
it's on GitHub with all the other stuff.
Okay.
Okay, so anyway, so what's the value sent? This master slave, I think we went through that. Okay, and then we talked about exchanges and transactions. I still to this day get confused by this. I get tripped up by this. An exchange is 1 byte, right? But I mentioned 1 byte exchanged, right? But a transaction is where you hack the SPI protocol to try to make it do not just an exchange, but like a programmed I/O, right? A read or a write operation, right? And a transaction is multiple exchanges, right? But those, I still get those wrong to this day. So a transaction, for instance, would be, so here's an example of a read transaction, well, I said read operation, that should say transaction. So the idea is that the slave select is low for 16 cycles, not 8 cycles, because there's 2 bytes exchanged. The first byte is the header, the second byte's the data. When the header is sent from the master to slave, it's just an outgoing bits, no bits come back, and thus that's why this guy's a flat line. But then on the second exchange, the read data comes back from the slave, right? So you give the slave some time to chew on the address that you send it so it can look up the proper word to send back, right? It can't be done simultaneously because it's impossible. You've got more than one register on the slave. You can't expect the slave to look up to decode a register value before you actually send it the address of the register, right? So as a result, there has to be 2 exchanges. And as a result, the functional utilization of the bus is only 50% because we don't use 1 bit line on the first exchange and we don't use 1 bit line on the second exchange. Now you might ask, well, why are you showing data there on that second exchange on SDI or MOSI? I don't know. That's because it's not my design. It's not my. We pulled that timing diagram from a data sheet. That's one I didn't generate. Okay, and of course, write is when you just have outgoing data. Now, one of the problems with this, by the way, is if I do a write transaction, say, how do I know the data I wrote was received by the slave? I don't. There's no way to know. And that's one of the horrible weaknesses of SPI. There's no way to acknowledge. There's no robustness whatsoever. You just send the data out there and you just hope that someone got it. But there's no way to know. Of course, you could write and then read it back, right? But that's something that would be handled at the application layer. Okay, so here's an example question. We already went through that last time. I'll skip through this. Unless anyone has any questions, any confusion about that? Okay, so then, okay. So, all right, so let me talk briefly about Lab 1. We don't have, like I said, I don't have it ready to go. We'll officially send it out. And the lab, we'll give you a lab sheet on Tuesday, and we'll give you all day Thursday to work on it. But the objective here is we want you to write a software-based SPI decoder, meaning that we're going to give you a trace file. So we're going to give you a textual version of a timing diagram, essentially. And then you just read that timing diagram as a text file and then interpret it as transactions. And then you would just print what the transaction is. So you would say, read from address 11, the data was 12, or write to address 30 with data 40, right, for instance, right? And you would just print that out, right? So the signal trace file is a little confusing at first. Basically, the idea is that the trace lists the state of all the signals in tabular form, but it only prints it only prints a row. It only prints the new state of the signals whenever a signal changes, right? So what ends up happening is that your sample times may not necessarily be at uniform intervals, right? So in this case, you may have a sample at 1 millisecond, a sample at 3 milliseconds, a sample at 4 or 5 milliseconds, and it may skip to 8 milliseconds, right? So that's the way that the trace file is organized. And then this is the way it actually looks. So it's just a text file, and at the top, the top is the number of samples and basically number of rows, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, there's, it starts here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 samples, right? And then the first row is the names of the signals, right? So in this case, we have, instead of having, yours is going to say S clock, MOSI, MISO, and slave select. In this case, this is a more generic one where we just have clock and then signals labeled S0 through S7, right? And so those are essentially you could think of those as the columns, except the problem is that there is no column header for time, which is really the first column. So as a result, these things are shifted over to the left a little bit, makes it a little hard to read. The next column is the number of bits in each one of those signals. Obviously, with SPI, they're all 1-bit signals. We've done other versions of this where we looked at other protocols that had more than 1 bit, but we don't use those anymore. And then every line is just time, and then followed by the state of each signal at that time, right? Now, it turns out you don't have to parse that directly, though, because, highlight all that. You don't have to parse all that stuff directly because we are going to provide you with an API to read those if you want to use it. You don't have to use it, but we're going to provide an API. We have both a C and a Python version of it. We were talking about not deleting, last time no one used the Python one, so I think everyone's more comfortable with C, but they're similar. So basically you just declare this structure called waves, and then you, as a pointer to a waves object, and then you call parse file standard in. And you might say, why standard in? Why not give it an actual file? Why not give it the file where the waves are? Well, because we have an auto grading framework that's going to send these waves in through standard in. So you want to use standard in as the file, right? It's going to, you want to expect the data to come in on standard in, and then there's basically just 2 functions you need at that point. There is a function called next edge, right, which will give you the time. It returns time as a float. Returns time in seconds of the next edge starting from this parameter called after, right? So every time you call this after argument is going to be advancing forward in time, right? So you're going to basically say, okay, I found one edge, now I got to get the next edge. So you're going to start where you found the previous edge to find the next edge, right? And then you're going to start at that edge time and to find the next edge, right? So you're just going to keep marching it forward, right? So that after is where you're starting from. And then these pause edge and neg edge are Boolean flags that allow you to tell it which edge you're looking for. Positive edge, meaning rising edge, negative edge, which is the rising edge, or either edge. If they're both 1, it'll look for either edge. And then, of course, the name of the signal that you're interested in this case, clock, right? And then the first parameter is just the my waves, the pointer to the my waves object, right? And then there's a signal at. So this will just tell you the signal, the state of the signal at a certain time. So the name of the signal and the time, right? And so with just those 2 functions, you can just run through the trace and interpret it. So what you're going to be looking for is, obviously, initially you're going to look for the falling edge of slave select, and then you're looking for either the rising or falling edge of clock, depending on how the channel is set up. And then at each one of those falling or rising edges of the clock, you look at the corresponding value of MISO and MOSI. Make sense? That's basically the idea. Now, there can be, in the lab, in the data that we give you, we have test data for you, there can be multiple transactions, right, inside of one trace file. Okay? So you might say, well, then how do we know when we reach the end? If you reach the end, then next edge will return infinity, I believe. I got to double check that. I think it's INF. It's in the lab sheet. But this will return an error code if you tell it to find the next edge and there aren't any more edges, right? Because you're at the end, right? So that's the way you'll know you're at the end of the file. Okay. Okay, so then in the lab sheet, the lab sheet, we mentioned this last time, but we didn't emphasize it much, but doing transactions over SPI, as I mentioned, is basically a hack. And I say it's a hack because the protocol itself does not accommodate transactions. The protocol only accommodates exchanges. The only thing the SPI protocol defines is how you can do an exchange. If you want to do a transaction, then that's up to you. You have to come up with your own higher level protocol that sits on top of SPI. And as a result, that's going to depend on peripherals. You know what I mean? Like it's not standardized. You might buy an accelerometer that does it one way, and you might buy an OLED display that does it another way, right? So in the lab, we define our own protocol. And by protocol, what I really am talking about is the header byte fields, the header byte organization, field structure, whatever you want to call it, the way the bits are, what each of the 8 bits represent in the header. So in this case, bits 7 down to 2 are the address. So that's 6 bits, 6-bit address. So the address can obviously just be 0 to 63 because it's 6 bits. And then bit 1 is read or write flag, and bit 0 is a single or stream flag. Okay. If stream is 1, that means that I want the data part of the transaction to be multiple bytes, not just 1 byte. Okay. However, there's an additional thing we throw in here is if the stream is 1, the next byte, the next exchange, is the master telling the slave how many bytes are part of the stream. So it's a length field, which is a whole 8-bit length field, at which point then the subsequent exchanges will be either the read or write sequence, right? So obviously in that case, the address is the starting address because, you know, you give it a starting address, you give it a length of the transaction, and then the transaction bytes, right? So that's a little different than what we showed in the last lecture because, like I said, these transaction protocols are arbitrary, right? Okay, so now in this case, we're not doing a stream. So here's an example where we send an address, which is 6 bits, and we want to print this address in hex. But yet hex is groups of 4 bits. So in this case, when you convert this to hex, this would be a 1. You have to group 4 bits starting from the right and moving to the left. So the first group of 4 bits starting from the right is 1, and then 1, right? So the address in hex would be 1, right? Or in binary is 0, 1, 0, 0, 0, 1, right? And then the read bit is a 0, which means we're doing a read. And the stream bit is 0, which means we're not streaming. And so this is going to indicate a read. And so in the next half of the transaction, remember there's 2 exchanges, so slave select is low for 16 cycles. In the last 8 cycles of the slave select, the master sends stuff, which is just all zeros because we don't care, and then the slave sends back the data, which is in hex would be 110 or 1A in hex, right? So your output from your program should just be RD standing for read, then the address 11, and then the data 10, right? Okay, so then this is a write, same idea, except in this case, because it's a write, your program has to recognize after having read the first 8 bits coming out of MOSI that this is a write. So the next 8 bits should be read not from MISO but from MOSI. We read it from MISO before because it was a read. Now we read them from MOSI and we read 39 is the data. So you would print write 3B 39, right? Okay, and then if there's a stream, so this gets kind of wild. So in this case, if you count the number of cycles that slave select is low, it's actually 8 times 4. So there's 32 cycles here where slave select is low because there are 4 transactions happening here. See, I screwed it up again. There's 4 exchanges, 1 transaction consisting of 4 exchanges. Each exchange is 8 bits, so 4 times 8 is 32. So we have 32 clock cycles here. And so in the first byte, you get an address of 1, 4 in hex. Then you say read write bit is 0, which means it's a read, and the stream is 1, okay? So this indicates to the slave that I want to read a stream starting at address 1, 4, right? Okay, so but you have to then indicate to the slave, well, how long's the stream? How many bytes are we reading starting at address 1, 4? So that comes in the next 8 bits on MOSI, right? Which is 2, right? So I'm going to do 2 bytes, and so then the next 16 cycles, 2 times 8, I'm going to read not MOSI, but MISO, because it's a read. I'm expecting data to come back. And each of those bytes is going to be 0F and then B0, right? So then your program then should print read stream 24, which is the address, and then the 2 bytes that it read would be 0F and B0, right? So it's just a matter of, using those commands to read the waveform and then just interpreting the data or the functions. And then here's an example of a streaming write, same idea. Okay, and then, so the lab is organized as 3 parts. The first part is basically just doing single reads and writes. The next part is streaming reads and writes. And then part 3, you have to add the capability of changing CPOL and CFA because we use default values of CPOL and CFA in the first 2 parts. The reason why there's 3 parts is because this is the way that we assign the partial credit. If you get like all of part 1 working, that's actually the lion's share of the points. But if you want to, like basically it's like a C if you get part 1 working, it's a B if you get part 1 and 2 working, and an A if you get part 1, 2, and 3 working, right? So in the case of part 3, you have to be able to read the values of CPOL and CFA. They're actually stored, I forgot to mention this earlier, those are stored in the trace file, right? You don't, in the first 2 parts, you don't even read them, like you just ignore them. But they are actual constant signals in the trace file. So you can read those at any time, like at 0, right? And they'll tell you what the CPOL and CFA is. So you have to slightly change your code, right, to accommodate the variations on when you have to read based on CPOL and CFA. Okay, and that's part 3. Alrighty, so, okay. Cool, any questions about that? Okay, did you want to say something?
I just want to use for help because I can't find the repository can't find the surfaces on your hub page.
Oh, it's called Chic, Software Hardware Interfacing course.
This is on the RTS laboratory links on your GitHub.
Okay. Well, I'll show you after class. Yeah, we'll assign it on Tuesday. It's okay because it's not a big deal because I want to start doing lecture on Tuesday and lab on Thursday, so we're okay. Yeah. So it'll be like I said, you guys will have all day on next Thursday to work on it. So try not to forget the SPI stuff. So because I'm going to switch topics now and talk about UART. So you guys might have heard of UART. It stands for Universal Asynchronous Receiver Transmitter. This is the protocol that's used for text, usually terminals. So this is also a this is a serial protocol. 1 bit at a time is sent through the channel. And like SPI, it's bidirectional. So there's a bit flowing in both directions. So 2 data bits in opposite directions, right? But there's no clock. So it's asynchronous. It's an asynchronous protocol. And there's no slave select. So how do you know when a transaction starts? So the way it handles that, it uses start bits and stop bits, right? Yes?
Probably you should ask them to do it in C instead of Python because they anywhere will be use C in lab 2, lab 3. So maybe just let them do lab 1 in C and don't.
Yeah, so here's the deal. So 5-10 years ago, there was a perception that Python was going to take over all programming. Everyone would become a Python programmer. So we would switch 145 and 146 to Python. No one would ever use Java or C again, right? Because Java is clearly the best programming language ever invented in the history of the planet Earth, right? That's what any Python programmer will tell you, that there is no reason why anyone would use any other language but Python. All the machine learning that's done at every company, at every university, all Python. All scientific code now, Python. All data analytics code, Python. All big data code, Python. Everything is Python. Python is the greatest thing ever conceived by humankind. And so, I kind of bought into this because I had a student, Charles, who basically agreed and argued that voraciously, that you would be a moron to use any other programming language because Python is clearly just the most beautiful thing ever created. Now, of course, I've been told that by Haskell programmers too, and functional language programmers, and Rust programmers, and Go programmers too. But it seems like Python had the most sort of religious zealots on its side. And so we assume when we developed a lot of this course material that probably 85, 90% of the class would want to use Python for this project, right? Because that's, why wouldn't you? You have to, right? Then we taught it last semester. So we provide a Python and C API. And then last semester actually, because I taught this in spring, I don't think anyone used Python, okay? Meanwhile, my grad students hate Python, all of them. Not one of them will use Python. Well, except for Iftikhar. I've got one new one, right? But Angela hates it, won't touch it, refuses to learn it, refuses to read it, refuses to try it, refuses to think about it or discuss it. Don't know why. Like, I don't understand the weird irrational obsession with Python that some people have, because it's slow as hell, and every time I've tried to use it, it never works because it always says you don't have this module or that module, and you try to do machine learning and it says you don't have TensorRT and there's no way to get it. Even though I'm using the most common distribution and the most common GPU on Earth, it still never works right out of the box. So I don't understand the irrational love for it, and on Angela's case, I don't understand the irrational hatred for it either, because it's designed as a kindergarten programming language. In fact, it was designed originally to replace BASIC, which used to be designed as the first programming language someone would learn. BASIC was my first language. It's just line numbers and print and go to, and that's it, right? It was designed for kindergartners to learn programming. That's what Python's original purpose was, and then it became the greatest, most advanced thing on Earth. But originally, it was designed to replace BASIC and Logo, which were the two teaching languages, right? So clearly, Angela could learn that if she tried, but she doesn't want to. And at the same time, we have people saying that, you use MATLAB? What a noob, like, what a llama, So I don't get it. I don't get either side. I don't understand it. So how many of you guys, just put your hands up, would you use Python for this project? Any of you? Maybe one, two, okay. So Angela wants to ban Python. Angela wants to ban Python from the class. She wants to excise it. She wants to annihilate Python. I don't care because, so our grading scripts will use either one. Charles's grading script will literally just choose, it'll recognize whether you wrote it in Python or C and just apply the proper thing. So it makes no difference to us. Okay, anyway, sorry for the tangent. Okay, so UART is a really simple protocol because it's designed to be slow. It's designed to be no faster than you can type. It's designed to run at typing speed because it's a textual protocol. So the way it works is there's one bit and that flows in each direction, and that bit idles at 1 all the time. So the idle state is active high, active 1, logic 1. And then the way that a transaction is transaction exchange, a transmission. The way a transmission is indicated is through a start bit, which is logic 0 for 1 clock time, 1 bit time, right? The problem is what's a bit time? Because there's no clock. How do you know what the bit time is? Well, it uses a kind of insane approach where you basically just have the two sides of the channel agree ahead of time what the speed of the channel is, and that's called the baud rate. And so the baud rate can be, 9600, which is 9600 bits per second, or 19,200, or there's a variety of baud weights, but it caps out at about 50. I think usually you see the highest you see it is like 50,000 bits per second, 50 kilobits, right? Which would have been slow in 1981. But again, this is designed to be as fast as you can type, so that kind of makes sense. If you're a really fast typer, you might be able to type at 50,000 characters per second, right? So, or bits, actually that's bits per second, right? So you have to divide by 8. But anyway, so that's the idea, and then you go low. Now the problem is that there's two problems with this. Number one, if you're like me and you don't read manuals, you never know what the baud rate is supposed to be, so it's a trial and error process. right? Every time I connect a terminal to my FPGA, I got to try 96. Does that work? No. 19.2, does that work? No. 38.4, does that work? 38,400. I got to continuously try, and I've wasted hours and hours of my life with this horrible trial and error where I'm trying to guess baud rates. But
motivation to actually get and read data sheet.
right. So that's the problem. In the FPGA, it's really obnoxious because if you use the JTAG over USB connection, which is what most people do, that's one speed. But if you physically connect a serial line to the FPGA, it uses another speed, right? So it's always wildly confusing. The other problem is that you have this issue where there's no guarantee, even if you match speeds, there's no guarantee that on the receiving side, the receiver is going to try to read while the driver is transitioning the bit. There's no guarantee that you won't go into metastability on the latching, on the capture register on the receiving side. Now, the thinking behind this by the UART people is that yes, there's no guarantee of that, and you will get bit errors. They're unavoidable because you can get metastability because there's no guarantee that you won't violate the setup and hold time on the receiver end, right? However, if we make the bit times ginormous by having a very low bit rate, right, channel rate, the likelihood of that happening is kind of small, right? So for example, if you tried this on SPI, it would be horrible because SPI is megabits per second, right? But if you try this on kilobits per second, yeah, you'll get some errors, but you probably won't notice it. It'll just be a glitch here and there on your terminal, right? That's the thinking, right? Okay, so anyway, after the start bit, then you put 8 bits in, or however many bits you specified as the number of data bits. It's usually 8. And then there's a stop bit, which is 1 bit time of logic 1. And the stop bit is literally just to separate consecutive. Like if you try to put consecutive characters one after another, the stop bit guarantees that in between each character, each byte you send, there will be 1 bit time of 1 for the stop, followed by 1 bit time of low for the start before you send the next bit out, right? And UART usually goes from least significant bit to most significant bit. So now this is the opposite of SPI. So now when you read these bits, you have to reverse them. You have to read them. Here you're reading from left to right in time, but on paper you're going to have to fill them in from left to right here, but you're going to have to fill them in from right to left when you write them down, right? Because they're coming in opposite order. Okay, so I already covered that. Okay, then there are some optional features here. You can optionally have a parity bit that comes after the data bits. Okay, so this basically adds an extra header bit, overhead bit, right? So it takes 8 bits to send a byte, but you have to waste a bit time for the start bit, and you have to waste a bit time for the stop bit. And if you have a parity bit, you got to waste another bit for that. So now you have to send 8 plus 3, 11 bits in order to send one 8-bit byte. So essentially what you're doing is you're encoding an 8-bit data byte into an 11-bit frame, right? So this is the reason why the baud rate, which is the rate at which you send the bits, is going to actually be higher than the rate at which you can send the bytes, the data bytes, because of this overhead, right? So if you want to figure out the number of data bits per second, it's going to be the baud rate multiplied by 8 over 11, because you only get 8 real bits out of 11 actual bits that you have to send, right? You only get 8 data bits for 11 actual physical bits you send, right? Okay, so anyway, so that's the difference between baud rate and throughput. Baud rate is the line rate that defines the bit time, how much time you spend in each bit, or how much time the receiver should give, to read each bit, time slot. And throughput is how many actual data bits you can push through, right? Okay, now let's go back to the parity bit here. So the parity bit's a bit confusing. You can set it up for odd parity or even parity. So the parity bit is designed as an error detection because it's there specifically because of metastability. Because if it's asynchronous and there's no way to guarantee that the clocks, you can guarantee the frequencies of the clocks on both sides are the same, but you can't guarantee the phases of the clocks on both sides of the channel are the same. And because of that, there's no way to guarantee that you won't enter metastability. And because of that, it's a good idea to have a parity bit, because a parity bit allows you to detect errors, right? And the way the parity bit works is that if it's an even parity, and again, this is something you have to establish ahead of time, right? You have to, the sender and receiver got to figure out, are we using parity? Are we doing even or odd? What's the baud rate, right? All this stuff has to be pre-negotiated somehow, right? Not really clear how to, again, you have to look it up and then set it up manually, right? The parity bit, if you have even parity, that bit will be 1 if there's an odd number of bits set to 1 in the data, which is totally counterintuitive, right? In other words, I'm going to set my even parity to true if there's an odd number of 1 bits in the data. What's up with that? It makes no sense. Well, the thinking behind that is if you have an even parity bit, what you're supposed to do is count the number of 1 bits that are in the data and the parity combined, and that should be an even number, right? And so as a result, if my byte I'm sending has an odd number of 1 bits, I'm going to set the even parity 1 to make the overall number of bits 1 bits even. Does that make sense? And then odd is the same way. Odd, I would set odd to 1 if there's an even number of 1 bits in my data, because once I do that, now I'm guaranteed to have an even number of overall bits. Now you might say, well, sure, but that includes the start and stop bit too, right? No. You got to forget about those. Forget about the start and stop bits. They're not part of the parity. They're not part of the data, which again confuses things even more, because if you're looking at a timing diagram, you're going to see the start and stop bits, and you're going to see the data bits and the parity bits. And what are we counting here? You got to only count the bits in the data and the parity for the parity calculation. Forget about the start and stop. Those are only for control purposes. Okay? Yes? What's that? No, they're only used to indicate the start and stop, so they're not considered bits. They're considered control signals, start and stop. Start and stop bit. They call them start and stop bits, but they call them that because they consume a bit slot, in time, 1 bit's worth of time, right? Sorry? No, well, no. This is typically done. This is handled in the hardware generally, unless you're bit banging. If you're bit banging, you would program it, but it would still be not technically part of the application. It's part of the protocol. Yeah, it's part of the protocol. It's defined in the protocol. Okay, so here's here. Oh, and one other thing. I forgot this too. There's always going to be 1 start bit, but you can have up to 2 stop bits. What does that do? Having 2 stop bits, all that does is if you're sending consecutive bytes. Now, by the way, if you're getting consecutive bytes on UART, it means that someone's like dumping text to you, right? But if you're typing, you're not sending consecutive bytes because there's going to be time in between your keystrokes, right? There'll be dead time between the keystrokes, right? But if you are sending consecutive bytes, like if you're printing out a directory listing or something over a UART channel, by having more stop bits will effectively, that's going to separate the bytes being sent more by a little bit more, right? And this is just for, presumably it's for signal integrity purposes, right? Generally speaking, in practice, I've never seen 2 stop bits used on any of my FPGAs or Arduinos or DSPs or any of the chips I've used. It's always 1 stop bit. But you can have more than 1 stop bit. So basically, ahead of time, you have to agree on the baud rate, number 1, number of data bits, if you have even parity, odd parity, or no parity, and the number of stop bits. These are all things that have to be set up beforehand because they're all required to communicate with UART. Okay? So here's an example. This is 7 data bits, least significant bit first. And as I mentioned, least significant bit first is I think, always the case for UART. No parity and 2 stop bits. So, bless you. So now in these timing diagrams, by the way, I generated these timing diagrams and they show a byte being sent on transmit and receive simultaneously. that's usually not ever going to happen, right? I'm showing it this way just because it makes it look like SPI a little bit, right? And as you might imagine, I use the same code. I recycled some of my SPI code. Now this can happen if you're doing, synchronized bidirectional, bytes on UART, but you usually will just see these channels are usually kind of independent of one another, right, in practice, okay? So anyway, this is start bit. You can see the start bit there, right? There's the start bit. And then 7 data bits is 0, 0, 0, 0, 0, 0, 0, 1. So I'm sending a 7-bit data of the value 1. There's no parity, and then there's my 2 stop bits there, right? And then same thing on the receive side. I've got start, and then 1, 1, 1, 1, 1, 0, 0, and then stop. Okay? 2 stop bits. Okay, so now I mentioned that when you read those bits, when you read the data bits, you got to reverse them. So if I read 0, 0, 0, 0, 0, 0, 1, that's actually hex value 40, right? Because I have to first reverse them, and then you have to read them in groups of 4 starting from the right. So that would be a 0 hex digit, 0, 0, 0, 0, that's 0, and then should be a 2, actually. Yeah, that should be a 2, not a 4. I don't know how I never noticed that before. Let's fix that. Okay. Okay, everyone okay with that? Okay. All right, so here's 9 data bits, even parity, 1 stop bit. Now in this case, I've got what's called an erasure, which is where there's an error here, and somehow the receiver, actually technically the transmitter, if I'm a transmitter, then on my receive line, I'm getting a signal back, right? And somehow I know that this bit is garbled somehow. I know it's wrong, right? So the question is, can I figure out what that is? You can actually fix an erasure with a parity code, right? Now the problem is, I don't know if UART, I'm actually not sure if any UART hardware actually has this ability to know a bit is wrong. It's possible because, like I said, if the flip-flop that's receiving this goes into metastability, I think there is a way to detect that potentially, right? So if you have a timing error just because the phases just happen to, don't work out, I think there is a way, but I don't know how common this is. But just for the sake of argument, if I knew that was an error, you can actually fill it in. So the way you would do that is you would just count the number of 1 bits here between the data and the parity. The question is, which are data and which are parity? Well, I'm going to skip the start bit, right? And then I've got 9 data bits and 1 parity bit. So I'm counting 10 bits here. I'm counting the number of 1 bits in the 10 slots, right? So starting here, I've got 1, 2, 3, 4, 5, right? 5 1 bits. And then this is the stop over here. So 5 1 bits. So that's an odd number. And I'm supposed to have even parity. So that missing bit should be a 1, right? It had to have been a 1, right? Assuming there's only 1 error. If there's multiple errors, then parity is really only designed to guard against a single error. If you get 2 errors, you can get fooled into thinking it's good. Yes?
So you can't detect where there's an error, you just ask again, right?
Yeah, there's no retransmission built into the protocol, but I think usually with UART in practice, if there's an error, I don't know. That's a good question, actually. I don't know. How does it report the error to the user? I don't know. That's a good question. We could find. So if you look up the data sheet on the Atmel 328P, there's probably a flag in the status register for that, is my guess. So you could probably read the status register, one of the status registers. Remember, like the example I showed you guys where I had like on fire, I had a flag that said, is the peripheral on fire? And there was a bit for that. There's probably a bit in the UART address space that says error. That's my guess. But that's a great question. I haven't thought about that. I mean, from the software perspective, I'm not sure how you check that. Okay, so this is all my annotations. All right. Here's a question. Assume a UART channel operates at a baud rate 9600 BPS, bits per second, and has 7 data bits, 1 parity bit, and 1. And by the way, if you have 9600 bits per second, what that really means is this is establishing how long one bit slot is. So you're taking the reciprocal, 1 over 9600 is the time that one bit slot occupies. The question is I don't know when to sample that bit slot. There's no guidance on when I should sample it, right? But at least you have the time for bit slots. If there's 7 data bits, 1 parity bit, and 1 stop bit, what's the data throughput? Let's see, 7 plus 1 plus 1 is 9, right? So you basically get 7/9, right, of your throughput. Oh no, 10. Oh, start, stop. 7 data bits, parity bit, stop bit. So there's 7 bits for every 10 bits. Yeah, so start, stop, and parity, right? Yeah, start, stop, and parity are 3 bits of overhead that you're adding to the 7. So it's 7/10. So you get 70%. So your throughput is only 6,720 bits per second of data on a channel that's giving you 9,600 bits per second. That's why they call it baud instead of throughput, because baud refers to the kind of the raw throughput that includes all the extra bits you have to include in there that aren't data. Okay, so here's another example. What bit is missing? This is odd parity. We've got 5 data bits, 2 stop bits. So forget about the 2 stop bits, forget about the start bit, count the 1 bits in between. So 1, 2, 3, looks like 3, there's 3 1 bits. And if there's odd parity, then that means that must have been a 0, right? Okay, 0, yep. Are there errors in the transaction below? Okay, we got to count. So pretty much odd parity, I'm seeing only 1 bit here. So that's checks out. And here I've got 1, 2, 3, 4, right? Because there's only 1 stop bit here, right? So there's 4 1 bits, right? 1, 2, 3, 4. Yeah, that's even. So yeah, there's an error there. There's an error on the second channel. Right, yeah, the received parity is incorrect. Okay, okay, so now we want to switch. Everyone okay with that? That's UART, not too complicated. Pretty simple, but it's designed to be simple. Yes?
On the slide you changed, I think you were correct the first time. Just it was the last bit was a 1 and you said it was 40. If it was 20, it would be a 6 bit instead of 7 bits.
Oh, it was 7 bits. Okay, I counted wrong. Thank you. Yep, thank you. That was right here, yeah. Yep, sorry. I think what happened is I didn't have the right number of bits on the little 6. Yeah, I see what happened. What happened was I screwed up the current slide. I screwed up this part. I had a bit missing in this little bit here. So there's 7 bits here. And I only had 6 bits down here when I reversed them. And that's why I thought it was 20. But you're right. If this is 7 bits, that should be 40 in hex. Yeah. Yeah, I was going off of what I had, the binary there. Okay. Okay, so let's switch back here to multi-SPI. And I know we should have covered this when I was talking about SPI, but there is a rhyme or reason to this, because this relates to driver circuits. So okay, so I mentioned earlier that SPI is generally you're going to have 1 master and 1 slave. There's just the 2 endpoints, right, on the channel. It is possible to have more than 1 slave. And there's a couple different ways to do that, and this is kind of neat. One way to do it is you can associate 1 slave select. You can have multiple slave selects and associate each one of those with a separate slave, right? And then the clock and the MOSI get fanned out, meaning that clock and MOSI are driven by the master and they go out to all the slaves. So all the slaves see the same clock and MOSI, but only one of them will actually acknowledge it because you have the individualized slave selects for each slave, right? The problem with this approach, though, is MISO, because there's only one MISO on the master, and so all the slaves have to connect to that MISO, to one MISO. Okay, now that's a problem because SPI uses what's called a push-pull driver design, meaning that every device that's connected to a wire on an output has to actively drive that output. They all have to be putting a 1 or 0 onto that output. And the problem is that if you have one driver that's trying to drive 0 on a wire and another one that's trying to drive 1, you end up with a pretty bad situation. You end up with a conflict, right? You got one guy trying to drive a wire down to 0 volts and one that's trying to drive it up to VDD volts, which is whatever the digital power supply voltage is. And what ends up happening is you end up with a short circuit, essentially. You short circuit the thing. And I'll talk more about that in a second, but to solve that problem, you can also use a daisy chain approach, which is where you have one slave select, but you have the slaves arranged in a daisy chain where MOSI comes out of the master, goes into MOSI on this first slave, and then MISO on the first slave, instead of going back to the master as it normally would, it just goes to MOSI on the second slave. And the MISO on the second slave goes into MOSI on the third slave, and the MISO on the third slave goes back to the MISO on the master, right? So that way, whenever I do a transaction, instead of just exchanging 8 bits, I have to exchange 8 times the number of slaves. So basically, you cycle all the bits through everybody, right? And the cool thing about that is that's how JTAG, if you've ever heard of JTAG, this is the way that FPGAs are configured. It works the same way. You basically have this gigantic shift register and you just send the bits through everything. You just worm the bits through everything. The problem is that in order to do, every time you do an exchange on here, it's got to not be, you have to multiply the number of bits per exchange by 3, right? So the transactions get really long. But that's the issue with that. Okay, but let's go back to the other approach. So going back to this slave select thing, this is the non-daisy chain approach. I mentioned that the MISOs get kind of shorted together here, right? The MISOs coming back, if they're not daisy chained, they're potentially in conflict. Oh, am I out of time? No, I got 10 minutes, okay. So you have this issue, and the problem is it's this issue of the way that the drivers are designed on SPI. The drivers are going to be, generally they're just inverters. They're CMOS inverters. And so the idea is that the output is connected to both a transistor that's capable of shorting the output to VDD and another transistor that's capable of shorting the output to ground. But because one's an NMOS and one's a PMOS, they're activated on different logic levels. And so that makes them, only one of them can be active at a time. Only one of these things will be turned on at a time. So one of these will be low impedance, connected the output to either through it, and the other one will always be high impedance, and they'll switch, right? So they're complementary. Makes sense? So at all times, this signal will always be, and again, I'm sorry, one thing I forgot to mention that's relevant, is important, is that the input to the driver, so internally on the chip, you have an output bit you want to send out to the bus. That output bit goes to both of these transistors, and because the transistors are activated on different logic levels, but they're getting the same input, they are only going to be able to pull their output to high or low, never both at the same time, right? So that's important. That's why CMOS logic is what all modern chips are made from. It's efficient in the sense that as long as you've got this thing, driving a 1 or a 0, there's no leakage. There's very little leakage internally in this circuit, right? Because you're basically just pulling the output up or pulling it down, right? When I say pulling it, I mean essentially shorting it. You short it to VDD or you short it to ground, right? The problem is that if you have 2 of these guys now on 2 different chips, if you've got two of these connected to a shared bus, so say this is MISO, well, it's this wire is MISO, right? Externally, it's MISO. So one of these guys is connected to me. They're both connected to MISO. If one of these guys attempts to pull MISO up, in other words, create a low impedance connection between MISO and VDD, and the other one attempts to create a low impedance connection between MISO and ground, you end up with a short circuit because it creates a low impedance path from VDD in one chip across that wire and then down to ground in the other chip. So you end up with a short circuit where you've got a path that involves two chips, but it allows current to flow from the power supply of one chip, gets dumped out, and sink into the ground of another chip, right? And so that's called conflict. Now, if they're both setting 1 or they're both setting 0, that's okay. But you can't guarantee that if you have two chips that are both connected to a single wire, right? So generally you don't have this. You would never do this. You would never have two chips driving the same wire. Okay, so basically what you end up with is so what you end up here is that if this guy is trying to drive a 1 and this guy's trying to drive a 0, your on resistance could be, for example, say 1 ohm effectively through this transistor, and the on resistance here could be 1 ohm, which means that you basically have a 2 ohm, not including the wire in between, resistance, right? So you could end up sinking, if this is a 5-volt system and you've got 2 ohms through that path, you could sink like say 2.5 amps of current out of one chip into the next if you end up with this. And then the problem is that wire would end up being halfway between VDD and ground. So it would be, the voltage would be in what they call the forbidden zone, which is at around 2.5 volts on a 5-volt digital system. So you wouldn't even be able to read, you wouldn't be able to interpret that as a binary value. And you'd be heating this thing up because you'd be pulling 2.5 amps across that wire and through those two circuits. So usually that results in smoking, burning up the system. As Charles used to say, you release the magic smoke from the chip. Not always. It just depends on how robust those things are to the heat. And it also depends on the... Now, the thing is, though, is that these transistors, the resistance of the transistor when it's on is a function of the size of the transistor, right? And transistors that are used to drive an off-chip signal are huge. They're made to be big, because the bigger the transistor is, the lower its resistance is, and the lower its on resistance is the more drive power you have, right? And the more drive power you have, the faster you can switch in the face of high capacitance on this wire. So these things are deliberately designed to be gigantic transistors. So if you short a connection through two giant transistors, you're going to have a lot of current, and that could potentially damage the chip. Okay, so what do we do about it? Well, what you can do is you can put a tri-state buffer inside these circuits that allow you to electronically disconnect. You can disengage, right? So a tri-state buffer is just two transistors in parallel, which allow you to basically disconnect, right? So what that means in terms of like, for example, in System Verilog, the way that you would represent that is through what's called a high impedance. You set the circuit to high impedance, which means I'm disengaging, I'm disconnecting myself from this wire, and so the voltage on that wire would be floating unless another circuit were to start driving it. So you could create a multi-SPI system if all of the SPI MISO connections had this capability of this tri-state. The problem is that it's expensive to do that. It's expensive to have all this. Plus, there's also still no guarantee that the chips may, erroneously think they should both be talking, and they may turn on two tri-states, and then you still end up with a short, right? So it's not a great solution, right? So a better way to do it, there's a much better way to approach this, and it's called an open drain type interface. And an open drain is where you get rid of the pull-up transistor. And that way, each chip is only capable of shorting its output pin to ground or not, right? Making it essentially high impedance. But then you have a resistor that's put somewhere up to ground, connected to the wire up to VDD. Okay, that's a pull-up resistor, right? And you can size that however you want, but generally, you want it to be about, 10 kiloohms or something like that, right? And the idea is that if none of the chips that are connected to that thing want to transmit, they just turn off their connections to ground. They turn off their pull down, right? And then that wire then will naturally look like a logic 1 because it'll be connected to VDD. Now you might say, no, it won't. There's a resistor there. You'll get a voltage loss with that. You'll have a voltage drop over that. Yeah, you will, but not much. You might see, like, instead of 5 volts, 4.9, but it'll be high enough, right, to be considered a logic 1, right? And then if you want to pull down, you can pull down, but then if 2 chips decide to pull down at the same time, no biggie, right? Because you just pull down and you end up with still a 0 either way, and the most current you're ever going to, the current that you get sync from this thing will be limited by that resistor, will limit how much current that you're pulling down whenever you're trying to set the bus to 0, right? Does that make sense? And so that's the way you can get around this risk, and you can have multiple slaves on the same wire. And that's the solution that's adopted by the next protocol that we're going to talk about, which is I2C. So we'll cover that in class on Tuesday.